All right, in this section we're going to talk about subspaces. Basically, a subspace is just a vector space that happens to lie inside of a bigger vector space. Um, let's look at the definition. It says, let V be a vector space if W is a subset of V, and W is closed under the same operations defined in V, then W is a subspace of V. This should be V. So before we go through these examples here, let's I want to look at one example. Here's the plane R2, and we've already seen that R2 is a vector space. Well, let's look at the line that goes through the origin. I'm going to do the line y equals x. So if we have y equals x there, and we look at any vector that lies on there, we look at the set of all vectors that lie on this line. If you take any of them and scale them, they're going to get longer or shorter, and they might change direction, but they're still going to lie on the line. And if you add two of these guys together, then you're going to get something that's still on the line. So the vectors that lie on that line form a vector space, and they're within R2 and use the same operations. So the vectors that lie along this line, they are a subspace of R2. And there's nothing special about that line. You pick any other line that goes through in R2. As long as it goes through the origin, it's going to be a subspace. Now, if you don't go through the origin, it's not going to be a subspace, and you can show that it's not closed under addition or multiplication, but also the most obvious thing there is it doesn't contain the zero vector, so it can't be a subspace. So this list over here is 101. This is all of the subspaces of R2. R2 itself is considered a subspace of itself. And any line that goes through the origin, the vectors that lie along that line form a subspace. And the origin by itself is also a subspace, although it's kind of trivial, but it still fits the definition. If you look at this set that only contains the zero vector, if you take that and if you take this and multiply it by any scalar, you still just get the zero vector. And if you take it and if you pick two vectors out of here, well, there's only one. But if you pick this one twice and add it together, you still just get the zero vector. So the zero vector is considered a sub, or the origin is considered a subspace of this. Kind of an interesting thing here is R2 is two-dimensional. So this is 2D. The lines that go through there, those are 1D, one-dimensional. The origin is considered zero-dimensional. And the reason is, well, you know, in R1 you have left and right. And in R2 you've got left, right, up, and down. So in R2 there are sort of two axes you can move along. In R1 there's only one axis you can move along. But in just the origin by itself, I guess you'd call it R0 if you wanted to, there's no way you can move at all. So it's zero-dimensional. And by similar logic, if you look at R3, the subspaces of R3 are R3 itself, any plane that goes through the origin, any line that goes through the origin, and again the origin by itself. So those are all the subspaces of R3. Next up, I want to look at some verification, but we'll do that in the next video.